Hello and welcome back. Let me open tonight by taking something away from you, because I think the real version is better. You've seen a wormhole 100 times. A swirling tunnel of blue and white light, stars streaking past. A spacecraft hurtling down a corridor with walls made of something luminous and turbulent. That image is entirely wrong. Not exaggerated. Wrong in almost every particular. If a wormhole existed, and you came upon one in space, it would be perfectly still. There would be no swirling, no motion, no light of its own, no sound, no turbulence. It would make no more disturbance than a marble sitting on a table. And it would be a sphere, not a circle, not a hole, not an opening you could go around the back of. A sphere, hanging in space, the same from every angle. And on the surface of that sphere, you would see a different sky. Not a reflection, a view. Stars and darkness from somewhere else entirely, held in the surface, as though a bubble of another place had been set down in front of you. Around the edge, a thin ring of your own surroundings, stretched and warped, wrapping the boundary. You would not travel down a corridor. You would move toward the sphere, and the other sky would grow until it filled your view, and at some point, you would simply be there instead of here, with no sensation of transition at all. That's what the mathematics describes. And tonight, we're going to spend a couple of hours on whether the mathematics describes anything real, slowly, with nothing for you to remember and nowhere to arrive. Let's define the thing carefully, because the term gets used loosely. A wormhole is a hypothetical structure in space-time that connects two separated regions by a route shorter than the ordinary path between them. More precisely, a region of space with a peculiar topology, in which there's a tube, a throat, joining two locations that would otherwise be far apart. It's not a hole in the sense of an absence. There's nothing missing. It's a connection, a piece of geometry in which the fabric of space itself is joined in an unusual way. And the crucial thing is that the shortcut is measured within space, not outside it. You don't leave the universe and re-enter it elsewhere. You travel through a region that is genuinely part of space, and the distance through it happens to be shorter than the distance around. Whether such a structure can exist, and whether anything could pass through it if it did, are two entirely separate questions, and the honest answers are, in the mathematics, yes, and almost certainly not. The term itself was coined by John Wheeler in the 1950s, from the image of a worm boring through an apple rather than crawling across its surface. 2 points on the skin can be far apart along the surface and close through the interior. That's the intuition. And like most intuitions in this subject, it's helpful right up until it becomes misleading. To understand any of this, we need the idea underneath it, which was the great insight of the 20th century. In Newton's physics, space is a container. It's the fixed backdrop against which things move, an infinite, unchanging, featureless arena. Time ticks uniformly in the background. Objects move about within them, and neither space nor time is affected by anything. Einstein's general relativity says otherwise. Space and time form a single four-dimensional structure, and that structure is not fixed. It bends, it stretches, it responds to what's in it. Mass and energy curve space-time, and curved space-time tells matter how to move. Which means gravity isn't a force in the ordinary sense. A planet orbiting the sun isn't being pulled by an invisible rope. It's moving as straight as it can through a region where the geometry itself is curved, following the straightest available path in a shape that isn't flat. That's a radical reconception, and it's been confirmed exhaustively for over a century, by the bending of starlight, by the precession of Mercury's orbit, by the slowing of clocks in gravitational fields, by gravitational waves from merging black holes. And once you accept that space is a thing with a shape rather than an empty stage, an obvious question follows. What shapes are possible? Because if geometry can bend, perhaps it can also connect. Everyone has seen the standard illustration, and it's worth a chapter on what it gets right and wrong. The picture is a stretched rubber sheet with a heavy ball resting on it, creating a depression. Smaller balls rolled across the sheet curve toward the depression or circle it. What it gets right is the essential idea. Mass distorts the geometry, and objects follow paths determined by that distortion rather than by a force reaching out. What it gets wrong is nearly everything else. First, it uses gravity to explain gravity. The balls roll into the depression because real gravity is pulling them downward, which is exactly what's being explained. Second, it shows a two-dimensional surface embedded in three-dimensional space. Real space-time isn't embedded in anything. The curvature is intrinsic, a property of the geometry itself, not a bending into some higher dimensional room. Third, and most importantly, it shows only space bending. For everything at ordinary speeds, what we experience as gravity is overwhelmingly the curvature of time rather than space. The fact that clocks run at slightly different rates at different heights. So the sheet is a crutch. It conveys geometry responds to mass and almost nothing else correctly. And for tonight it matters, because the same illustration is usually extended to wormholes, folding the sheet so two depressions touch, which imports all of those errors and adds a new one. The fold requires an outside to fold through, and there isn't one. Let's spend a chapter on that point, because it's the hardest idea here, and it's worth having. When mathematicians say a space is curved, they don't necessarily mean it's bent through some larger space. Curvature can be defined entirely from within, by measurements made inside the space itself. Here's how. Draw a triangle. In flat space, the angles add to 180 degrees. On the surface of a sphere, they add to more. On a saddle, less. Or draw a circle and measure both its radius and its circumference. In flat space, the circumference is exactly 2 pi times the radius. In curved space, it isn't. Those measurements can all be made by someone confined to the surface, with no access to any outside, which means curvature is an intrinsic property, something the geometry has, not something imposed on it from a higher dimension. That's why the folded paper picture is misleading. Real spacetime has curvature, and it may in principle have unusual connectivity, and neither requires an external space for it to be curved or connected in. A wormhole, properly described, isn't a fold. It's a region where the intrinsic geometry has a tube in it, where you can walk in one direction and find yourself somewhere unexpected without ever leaving the space you started in. Which is much harder to picture and much more accurate. And if the picture won't come, that's fine. Nobody's does. The mathematics is clear, and the mental image simply doesn't exist. The idea entered physics in a paper by Einstein and Nathan Rosen, and what they were actually attempting is not what the paper is remembered for. By the mid-1930s, Einstein was uncomfortable with the way physics described particles. In the standard treatment, an electron is a point with charge and mass, and its fields become infinite at that point, which he considered a defect rather than a fact. So, he and Rosen tried to build a description in which particles were features of the geometry itself, with no singular points anywhere. Their approach was to take the known solution for the spacetime around a spherical mass, and to extend it mathematically, and they found something unexpected. The solution could be continued through to a second, separate region, connected to the first by a narrow bridge. They proposed that such a bridge might represent a particle, a structure with mass, made purely of geometry, with no singularity in it. The particle idea failed. It couldn't reproduce the properties of real particles, and it was abandoned within a few years. But the bridge remained in the mathematics, a valid feature of a valid solution, connecting two regions. It became known as the Einstein-Rosen bridge, and for 2 decades it was treated as a curiosity with no obvious physical meaning. Let's spend a chapter on the geometry itself, because it's stranger than the popular version. The solution Einstein and Rosen extended describes the space-time around a spherical, non-rotating mass, the same solution that describes a black hole. When mathematicians extended it as far as it would go, using coordinates that don't break down at the horizon, they found the full structure contains 4 regions rather than 1. There's the exterior universe we're familiar with. There's the black hole interior, which things fall into. there's a second exterior region, a whole separate asymptotically flat universe. And there's a fourth region that is the time reverse of the black hole, a white hole, which nothing can enter and everything must leave. The bridge connects the two exterior regions, passing through the middle. So in the full mathematical structure, a black hole is joined to a second universe by a throat. That sounds spectacular, and it comes with a substantial caveat. This describes an eternal black hole, one that has existed forever, in a universe with no matter falling in and no history. It's an idealization, and a real black hole formed from a collapsing star does not have this structure. But it's where the idea came from, and it's why black holes and wormholes are entangled in the popular imagination. Even in that idealized case, the bridge is useless, and the reason is elegant. The throat is not static. If you follow the geometry through time, it forms, stretches, reaches a maximum width, and then pinches closed, and the closure is fast, faster than light can cross. Which means anyone entering from one side would be caught in the pinch before reaching the other, and crushed at the singularity that forms as it closes. That's not an engineering limitation. Nothing travels faster than light, so nothing can beat the closure. The bridge is dynamically forbidden to be traversed by anything, ever. There's a second problem. Both mouths of the bridge sit behind event horizons, so you couldn't enter from open space and emerge into open space. You'd be crossing from inside one black hole to inside another, with no exit at either end. The two problems together make the Einstein-Rosen bridge entirely impassable, and for several decades that seemed to close the subject. Which is why the interesting question, when it was finally asked properly, was posed backwards. Not what does this solution do, but what would you have to add to make a passable one? Before we get there, a chapter on the man who named it and had his own idea about it. John Wheeler was one of the great physicists of the 20th century, and a gifted namer of things. He popularized black hole, coined quantum foam, and gave us the phrase, "it from bit." In the 1950s, working on the relationship between geometry and physics, he coined wormhole for these structures, and he took them seriously in a specific way. His proposal was that at extremely small scales, the Planck scale, which is about 10 to the minus 35 meters, some 20 orders of magnitude smaller than a proton, space-time might not be smooth at all. At those scales, quantum uncertainty in the geometry itself would become large. Space might be constantly fluctuating, forming and unforming tiny structures, including microscopic wormholes appearing and vanishing. He called it quantum foam, a picture of space-time as smooth at ordinary scales, but seething and topologically complicated at the smallest. It's a compelling image, and it's frequently repeated. It should be said clearly that it isn't established. It's a plausible expectation from combining quantum theory with general relativity, and we don't have a theory that does that reliably, so the picture remains a suggestion rather than a prediction. But it introduced the idea that wormholes might be a natural feature of space-time rather than an exotic construction, just unimaginably small. The modern era of this subject began in 1985, and it began because a writer wanted his plot to be defensible. Carl Sagan was working on the novel that became Contact, and he needed his protagonist to travel to a distant star and return within a human lifetime. His first draft used a black hole. He sent the manuscript to his friend Kip Thorne, a relativist at Caltech, one of the leading experts on this material, and asked whether it worked. Thorne told him it didn't, for the reasons we've just covered. The throat closes too fast, and there's no exit. But he became interested in the problem, and he turned the question around. Rather than asking what a given solution does, he asked, suppose you demand a wormhole someone could actually pass through. No horizons, no crushing forces, a reasonable travel time. What would the theory require in order to deliver it? That's a legitimate technique in general relativity, because the equations connect geometry to the distribution of matter and energy. Usually, you specify the matter and solve for the geometry, but you can run it backwards. Specify the geometry you want and calculate what matter would be needed. Thorne set the problem to his student Michael Morris, and the two of them worked it out. They published in 1988 in the American Journal of Physics, deliberately in a teaching journal, because they thought it made an excellent exercise for students learning the theory. The paper laid out the requirements for a traversable wormhole: no event horizons, so you could go in and come out; tidal forces small enough for a person to survive; a crossing time of reasonable duration. And they calculated what kind of material would produce such a geometry. The answer was specific and strange. To hold a throat open, you need matter with a property no ordinary substance has: negative energy density, as measured by an observer traveling through at high speed. They called it exotic matter, and the requirement isn't arbitrary. It follows directly from the geometry. Here's the reason. Light passing through a throat converges as it enters and must diverge as it exits. Ordinary matter, with positive energy, focuses light. That's what gravitational lensing is. To defocus it, spreading the beam outward, you need the opposite. So a wormhole throat requires something that repels light rather than attracting it in the gravitational sense. That single requirement has dominated the subject ever since, and everything that follows tonight is essentially about whether it can be met. Let's spend a chapter on exotic matter, because the whole question reduces to whether it can exist in useful quantities. Ordinary matter has positive energy density. A region containing a rock has more energy than an empty region. Gravity, correspondingly, attracts, and light passing near a mass is bent inward. Exotic matter would have negative energy density as measured in the relevant way, and its gravitational effect would be to push things apart and to spread light outward. Every substance you have ever encountered has positive energy density. Every particle, every field configuration, every arrangement of atoms. The requirement is what physicists call a violation of the energy conditions, a set of assumptions about how reasonable matter behaves, which underpins several important theorems, including results about black holes and about the beginning of the universe. Those conditions aren't laws. They're reasonable-sounding assumptions, and they were formulated when classical matter was the only thing under consideration. And here's the wrinkle that keeps the door ajar. Quantum field theory violates them. In small amounts briefly, under specific circumstances, and those circumstances have been produced and measured in laboratories. So the answer to, can negative energy exist, is not a clean no. It's yes, a little, under constraints, and the entire question is whether a little can ever be enough. The demonstration that negative energy is real comes from an effect predicted in 1948, and it's beautifully simple. In quantum field theory, empty space isn't empty. Fields fill it, and they cannot be perfectly still. The uncertainty principle forbids it, so there's an irreducible jitter everywhere, with fluctuations at every wavelength. Now place two flat metal plates in a vacuum, extremely close together, a fraction of a micrometer apart, closer than a wavelength of visible light. Between them, only certain wavelengths fit, the way only certain notes fit on a guitar string of a given length. Outside, all wavelengths are permitted, so there are more fluctuations pressing inward from outside than pushing outward from within, and the plates are pushed together by nothing at all. And the energy density in the gap between them is lower than that of ordinary empty space. Lower than nothing, which is precisely what negative energy density means. Not less than zero absolutely, but less than the vacuum. The Dutch physicist Hendrik Casimir predicted it, and it took decades to measure convincingly, but it was measured in the 1990s and confirmed repeatedly since. Two uncharged plates in a vacuum attract, and the space between them contains negative energy. That result is the entire reason traversable wormholes are still discussed. Without it, exotic matter would be pure fantasy. There are a few other routes to negative energy, and they're worth a chapter because they're all similarly marginal. One is squeezed light. In quantum optics, it's possible to prepare a state of light in which the uncertainty in one property is reduced below the vacuum level, at the cost of increasing it in another. Such a state has regions where the energy density dips below the vacuum value, genuinely negative, briefly, in small regions. It's routinely produced in laboratories and is used in gravitational wave detectors to reduce quantum noise. Another arises near the horizon of a black hole, in the process that produces Hawking radiation. The standard account involves negative energy flowing inward across the horizon, which is how the black hole loses mass. A third occurs for accelerating observers and in certain curved spacetimes, where the definition of the vacuum itself becomes observer-dependent and energy densities can be measured as negative. So negative energy is a genuine feature of quantum field theory, produced in several different situations, some of them in ordinary laboratories. The quantities involved are minuscule. The Casimir energy between two plates a micrometer apart is an almost unimaginably small amount, and the squeezed light effects are smaller still. But the principle is established, which is more than can be said for most exotic proposals in physics. Unfortunately, nature appears to police this rather carefully, and the rules are called quantum inequalities. Beginning in the 1970s and developed substantially in the 90s, these are theorems constraining how much negative energy can exist and for how long. The pattern is that negative energy is always accompanied by compensating positive energy, and the more negative energy you have, the more briefly it can persist, and the sooner the compensation must arrive. The analogy usually offered is an overdraft with aggressive terms. You can borrow, but the larger the loan, the faster you must repay, and the terms worsen with size. Applied to wormholes, the results are discouraging. For a throat a meter across, the negative energy required would have to be confined to a shell of extraordinary thinness, in some calculations, a layer far thinner than a proton, and the total amount is comparable to the energy content of an entire star. That's not a matter of better engineering. It's a mismatch between what the geometry demands and what the quantum rules permit, by a margin so large that most physicists working on this consider it effectively decisive. There are caveats worth stating. The inequalities are proved for particular field theories in particular circumstances, not in complete generality, and we don't have a full theory of quantum gravity to check against. So the door isn't locked, it's just very heavy, and nobody has found a way to move it. Let's put the requirement in perspective, because the numbers are worth stating plainly. The estimates for a human passable wormhole vary with the assumptions, but they cluster around something like the mass energy of a star, converted entirely into energy, and negative, and arranged in a shell of impossible thinness. To feel that, converting a single gram of ordinary matter entirely to energy releases about as much as a large conventional explosion. The total annual energy use of human civilization corresponds to converting a few tons. A star is around 10 to the 30th kilograms. So the requirement exceeds everything humanity has ever done by a factor with 30 zeros in it. And the energy must be negative, which no known process produces in bulk, and it must be held in a configuration nothing known could stabilize. Some later analyses found ways to reduce the requirement by allowing the exotic material to be confined to an arbitrarily small region. But the smaller you make it, the thinner and more extreme the shell becomes, and the quantum inequalities bite harder. So the honest framing isn't, we don't have the technology yet. It's that the required conditions may not be physically realizable at all by anyone ever. Which is oddly restful if you let it be. This isn't a door we're standing outside of, waiting for the key. It may be a door with no room behind it. There have been many attempts to construct wormhole solutions with less demanding requirements, and a chapter on them shows how the field has proceeded. One approach is the thin shell wormhole. Rather than distributing exotic matter through a region, you take 2 copies of ordinary spacetime, cut a spherical region out of each, and glue them together at the boundary. The construction confines all the exotic material to an infinitesimally thin shell at the join, which makes the mathematics tractable and lets you calculate exactly how much is needed. Another approach uses modified theories of gravity. In certain extensions of general relativity, with additional fields or higher dimensional terms or non-standard couplings. Wormhole solutions can be supported by matter that satisfies the ordinary energy conditions. Those are legitimate theoretical explorations. The difficulty is that the modified theories themselves are unconfirmed and generally constrained by other observations. A third approach uses rotating wormholes, or wormholes with electric charge, or various other complications, in the hope that additional structure reduces the exotic requirement. Hundreds of such papers exist. The general pattern is that the exotic requirement can be moved around, minimized, or shifted into an unconfirmed theory, but it has not been eliminated within standard physics. Even granting the exotic matter, there's a second problem, and it may be worse. A wormhole would need to be stable, which means that when something perturbs it, a passing particle, a beam of light, a spacecraft entering, it should return to its original configuration rather than collapsing. And the analyses generally find that these structures are unstable. Small perturbations grow, and the throat either pinches closed or expands uncontrollably. There's a particular concern involving feedback. Light entering the throat can, in some configurations, be focused and amplified, then return through the wormhole and pass through again, building up energy with each circuit. That's the same runaway as a microphone held too close to its own speaker, and it can destroy the structure. Some constructions have been shown to be stable for particular choices of the exotic matter's properties within a narrow range of parameters. Others are robustly unstable. So stability is an additional requirement layered on top of the exotic matter requirement, and it constrains the possibilities further. Which means that even in a universe where the negative energy was somehow available, holding the thing open against ordinary disturbances would be a further problem of comparable difficulty. Let's set the difficulties aside for a chapter and imagine passing through one, because it's a peaceful thing to picture. The first thing to say is that free fall has no sensation. If you were falling toward the mouth without engines running, you would feel weightless, exactly as you would anywhere else. The tidal forces, the difference in gravitational pull between your head and your feet, would depend on the size of the throat. Morris and Thorne specified their solutions to keep those comfortable, which for a human requires a throat at least meters across, and ideally much larger. So in a properly designed wormhole, you'd feel nothing. No pressure, no stretching, no heat, no resistance. The crossing time depends on the throat's length, which is a free parameter in the constructions. It could be meters or kilometers. In a compact one, the passage might take seconds. Visually, the other sky would grow from a sphere ahead of you to fill your entire forward view, while your own surroundings compressed into a shrinking ring behind. And then you'd be through in a different place, with the sky you came from now visible as a sphere behind you. The whole experience would be quiet, brief, and physically unremarkable, which is a recurring theme in this subject. The geometry is extraordinary. The sensation is nothing. Let's go back to the appearance, because it's the part most worth getting right, and the reasoning is satisfying. A wormhole mouth is a spherical region. Light from the other side emerges through it in all directions, and light from your side falls in from all directions. So from wherever you stand, you see the far region through a round patch, and the patch is round from every angle, because the mouth is a sphere rather than a disc. Walk around it and it looks the same. Inside that patch, you see the distant sky, distorted. The distortion comes from light bending as it passes through the throat. Rays entering at different angles emerge at different angles, so the far view is compressed or stretched depending on where you look within the sphere. Around the edge of the sphere, there's a ring showing your own surroundings, light from behind you that curved around the throat and came back towards your eye. That ring is warped and stretched, and it separates the two views with a sharp boundary. And there's no glow. A wormhole emits nothing of its own. Whatever light you see is light from one side or the other, redirected. If the mouth were moving relative to you, the far view would shift within the sphere as your angle changed, like a crystal ball showing a different part of the room as you walk past it. That's the whole optical picture, and it's been computed carefully. The careful computation happened for an unusual reason, and it's a nice story. In the early 2000s, Kip Thorne, the same Thorne of the Morris Thorne paper, became involved in developing a film that eventually became Interstellar. He insisted the visual effects be computed from the actual equations rather than approximated artistically. That meant tracing light rays through curved spacetime, following each ray backwards from the camera through the geometry to wherever it originated. The effects team wrote new software to do it, at a level of precision far beyond what film work normally requires, because the extreme distortions produced artifacts in standard rendering approaches. The results were good enough that the process generated technical papers. The team published in a physics journal on the rendering of black hole and wormhole images, and the work contributed to how such objects are visualized in research contexts. So a commercial film produced peer-reviewed physics, which is rare. And it gave us the first genuinely accurate images of what a wormhole would look like. The sphere, the distant sky held within it, the warped ring of local surroundings around the edge, all computed rather than imagined. It's still, by some margin, the best available picture of a thing that probably cannot exist. Suppose a wormhole existed somewhere in the galaxy. Would we notice? That's a real research question, and several groups have worked on it. The starting point is that a wormhole would have mass, or in some constructions, effectively negative mass, and mass affects passing light, so it would act as a gravitational lens. An ordinary mass focuses light, brightening a background star when it passes in front. That's microlensing, and surveys monitoring millions of stars have detected thousands of such events. A negative mass object would do the opposite, defocus light, producing a characteristic dimming with a distinctive shape, and, in some models, a dependence on wavelength that ordinary lensing doesn't have. So searches have been proposed and conducted, looking through microlensing survey archives for events with the wrong sign. Nothing has been found. The limits are not very restrictive. Such objects, if they exist, could be rare enough or small enough to have escaped. But the searches have been done and have come up empty. There have also been proposals for distinguishing a wormhole from a black hole at a galactic center, since a wormhole mouth would produce a subtly different shadow and different orbital dynamics for nearby stars. The observations so far are consistent with ordinary black holes, and there is no evidence of anything else. That question deserves a chapter, because it's an active line of research. The objects we call black holes are identified by their mass, their compactness and their effects, the orbits of stars around them, the X-rays from infalling gas, the gravitational waves from mergers, the shadow image by radio arrays. None of those observations directly confirms an event horizon. They confirm an enormous mass in a very small region, which leaves room in principle for alternatives, objects that are extremely compact but have no true horizon. Wormhole mouths are one proposed possibility, alongside several others. The distinguishing tests focus on what happens at the surface. A true horizon absorbs everything. Anything else would reflect or re-emit something. So people have searched gravitational wave data for echoes, faint repeats of a merger signal, delayed, which would occur if the object had a reflective surface rather than a horizon. Some claims of detection have been made, and none has survived scrutiny. Similarly, the images of black hole shadows have been examined for deviations from the predicted shape, and the ring structure would differ subtly for a wormhole. The results so far are consistent with ordinary black holes, and the space for alternatives is narrowing. But it's a legitimate program, and it's the only realistic route to observational evidence for wormholes, not finding one directly, but discovering that something we thought was a black hole isn't. There's an argument against wormholes that has nothing to do with exotic matter, and for many physicists, it's the decisive one. If you had a traversable wormhole, converting it into a time machine would be almost trivial. Here's the recipe, worked out by Thorne and colleagues in the same period. Take a wormhole with two mouths, both sitting near each other. Leave one where it is. Take the other and move it. accelerate it to a large fraction of light speed, take it on a long round trip, and bring it back. The traveling mouth has experienced less time than the stationary one because of relativistic time dilation, the same effect as the traveling twin. But the two mouths are still connected through the throat, and the throat's internal length hasn't changed. So the connection now joins two moments that aren't simultaneous. Step into one mouth and you emerge from the other at an earlier moment. Step the other way and you go forward. There's an even simpler version. Park one mouth near a very massive object where time runs slow, leave the other far away, and wait. The difference accumulates on its own. So anyone who builds a traversable wormhole has, whether they intended to or not, built a time machine. And it's that consequence, more than the engineering, that makes many physicists suspect the whole thing must be impossible. There's an important limitation that follows immediately, and it answers a question everyone asks. A wormhole time machine, once built, connects two moments, but it cannot reach any moment before the wormhole existed. If the connection is established on a Tuesday, then Tuesday is the earliest destination forever. You cannot use it to visit last year or any period before the machine was made. The reason is simply that the link is the wormhole itself, and it didn't exist earlier, so there's nothing to arrive through. The closed loops in the causal structure only exist in the region of space-time after the thing is switched on. That's a general feature of nearly every proposal in the literature. Whatever the mechanism, the device defines the earliest reachable moment. And it has an elegant consequence. It explains the absence of visitors from the future without requiring anything to be impossible. If no such device has ever been built, then no traveler could arrive here from any future, however advanced. So the usual question, why is history not crowded with tourists, dissolves into a technical detail about how the mathematics works. Which is a satisfying thing to lie with. The silence proves nothing at all. The strongest argument against all of this came in 1992, and it has the finest name in physics. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent closed causal loops from forming, thereby, as he put it, keeping the universe safe for historians. The mechanism he proposed is elegant. Consider a space-time where such a loop is about to form. Now remember that empty space is full of quantum fluctuations. Once a closed loop becomes available, those fluctuations can circulate around it, and each time around, the energy is amplified, blue shifted, gaining rather than losing. Then it goes around again, and gains again. It's the same runaway feedback as a microphone held too close to its own speaker, a small input fed back into itself, growing without limit. The result, Hawking argued, is that the energy density diverges precisely at the moment the loop would form. An enormous energy density means enormous curvature, which distorts the geometry, destroying the very structure that would have permitted the loop. The time machine self-destructs at the instant of its creation. He couldn't prove it in general, and he called it a conjecture deliberately. But it remains the leading reason most physicists expect the answer to be no. Not because the equations forbid it, but because there's a plausible mechanism by which nature would close the door at the last moment every time. Everything hinges on a theory nobody has, so let's spend a chapter on why that matters. We have two extraordinarily successful frameworks. General relativity describes gravity as curved spacetime and has passed every test for over a century. Quantum field theory describes the other forces and all known particles, with predictions confirmed to 11 decimal places in some cases. They don't fit together. Apply quantum rules to gravity itself, and the mathematics produces infinities that resist the usual methods of taming them. For most purposes that doesn't matter, because gravity is negligible for individual particles, and quantum effects are negligible for planets. The two theories rarely need to speak. But they must speak in exactly the situations we've been discussing: the interior of a black hole, the first instant of the universe, and the vicinity of a wormhole throat, where you have enormous quantum effects in a strongly curved geometry. So the question of whether wormholes are possible is in the end a question about the missing theory. If quantum gravity forbids them, chronology protection becomes a theorem rather than a conjecture. If it permits them under some conditions, the subject changes entirely. Candidate frameworks exist: string theory, loop quantum gravity, and others, but none is confirmed, and none has produced a decisive answer. Which means the honest response to tonight's question depends on physics nobody has, and might not arrive for decades or centuries. In 2013, two physicists made a suggestion that has occupied theorists ever since, and it connects wormholes to something that seems entirely unrelated. The suggestion is usually written as an equation of names. ER equals EPR. ER stands for Einstein and Rosen, the wormhole paper of 1935. EPR stands for Einstein, Podolsky, and Rosen, a different paper, published the same year, about quantum entanglement. Entanglement is the phenomenon where two particles are prepared in a joint state, such that measuring one immediately determines the outcome for the other, however far apart they are. It's been confirmed exhaustively, and it does not permit sending signals, but the correlations are real and stronger than any classical explanation allows. Juan Maldacena and Leonard Susskind propose that these two ideas are the same idea. Specifically, that two entangled black holes are connected by a wormhole, and, more radically, that entanglement in general is geometrical connection. That when two particles are entangled, they are joined by an unimaginably small wormhole. Einstein wrote both papers in the same year, and never suspected any relationship between them. That's part of why the proposal is so striking. Let's spend a chapter on the implications, because they're genuinely strange and worth sitting with. If the proposal is right, then space itself is not fundamental. Geometry, the distances and connections between places, would emerge from patterns of entanglement in some deeper description. Two regions are close together because their quantum degrees of freedom are entangled. Cut the entanglement, and the connection between them disappears. There's a striking calculation supporting this in a particular mathematical setting. If you gradually remove the entanglement between two halves of a system, the geometry connecting them thins and eventually pinches off. The space between them literally ceases to exist. That's led to the slogan that space-time is built out of entanglement, which appears in a great many talks and papers over the last decade. It's not established. The concrete calculations exist in idealized settings that don't describe our universe, and the general claim remains a conjecture. But it's taken seriously by a substantial fraction of theoretical physicists, and it's shaped the field. And notice what it does to tonight's subject. It suggests wormholes might be everywhere, connecting every entangled pair of particles in existence, at scales unimaginably small. Which sounds like good news for travel, and isn't, for a reason we'll come to. The immediate hope when this proposal appeared was that it might make traversable wormholes natural. It doesn't, and the reason is instructive. The wormholes implied by entanglement are non-traversable. They connect two regions, but nothing can pass through. The throat pinches faster than light can cross, exactly as in the original Einstein-Rosen bridge. That's not a coincidence. It's required by the physics of entanglement itself. Entanglement alone cannot transmit information. That's a theorem, confirmed in every experiment ever performed. The correlations are real, but you cannot use them to send a message. If entangled particles were connected by passable tunnels, you could. So the geometry has to be impassable, precisely because the quantum mechanics forbids signaling. Which is a rather beautiful consistency. Two entirely different descriptions, one geometric, one quantum, agree on the same prohibition, arrived at by completely different routes. And it means the proposal, if true, would make wormholes ubiquitous and useless in the same stroke. To make one passable, you'd need to do something beyond entanglement, and that's exactly what the next development explored. In 2017, 3 physicists published a result that made a wormhole traversable in a specific mathematical setting, and it's worth a careful chapter. The setting is a theoretical universe with different geometric properties from ours, a space with negative curvature, used extensively in theoretical work because it has a well-understood correspondence with a quantum theory on its boundary. In that setting, Ping Gao, Daniel Jafferis, and Aaron Wall showed that if you couple the two boundaries directly, establishing an ordinary connection between the two sides, the wormhole between them becomes briefly passable. Something can go in one side and emerge from the other. But the coupling is the catch. To arrange it, you have to send information from one side to the other by ordinary means, which means the wormhole doesn't get you anywhere faster than you could have gone otherwise. It's a shortcut that requires you to already have a longer path in operation. That's not a disappointment to the theorists. The point was never travel. It was understanding how information escapes black holes, and the result contributed substantially to that. But it does mean the headlines describing it as making wormholes traversable were misleading in the way that matters most to anyone imagining a journey. In late 2022, a paper appeared with an announcement that got enormous coverage, and unpicking it is a useful exercise. A team ran a quantum simulation on a small quantum processor, implementing a simplified model related to the theoretical setting just described, and reported observing behavior consistent with information passing through a traversable wormhole. The coverage described it, in many outlets, as creating a wormhole in a laboratory or holding one in a computer. That is not what happened, and the researchers themselves were considerably more careful than the headlines. What was done was a simulation, a quantum system engineered to have the same mathematical structure as a much simpler toy model, which in turn shares features with a theory that has a geometric description. No space-time was bent, nothing traveled anywhere. The processor sat on a bench doing ordinary quantum operations. Considerable criticism followed, both about the framing and about whether the simplified model retained enough of the original structure to be meaningful. A follow-up analysis argued that key features had been lost in the simplification. I mention it because it's a good case study in how these stories travel, and because if you've encountered the claim, it's worth knowing what was and wasn't done. Let's turn to a different question. Even if nobody can build one, could the universe have made one? The main proposal involves the very early universe. In the first instance, conditions were extreme enough that quantum gravitational effects operated on macroscopic scales, and if Wheeler's foam picture is right, tiny wormholes may have been forming and vanishing constantly. The suggestion is that a period of rapid expansion, inflation, could have taken one of those microscopic structures and stretched it to enormous size, freezing it into the geometry. That's speculative in several directions at once. It requires the foam picture to be right, requires a structure to survive being stretched, and requires it to remain stable for billions of years afterwards. There are also proposals involving topological defects, structures left over from phase transitions in the early universe, like cosmic strings, which have their own unusual geometry. None has observational support, and the same stability problems apply. A wormhole that formed early would still need something holding it open ever since. But it's worth noting that the natural formation route doesn't require anyone to build anything or to arrange exotic matter deliberately. It only requires the early universe to have produced something and the something to have survived, which is a different kind of long shot. Let's spend a chapter on fiction, because it has shaped how everyone thinks about this, and it has a specific reason for existing. The problem storytellers face is the speed of light. The nearest star is 4 light-years away. The galaxy is 100,000 across. Any story involving multiple worlds requires some way around that, or the plot takes millennia. So science fiction invents mechanisms. Some are frankly magical. Some borrow real terminology. Wormholes became the respectable option, because unlike most inventions, they correspond to something in the actual equations. A writer using one can point to published physics. The most careful example is Carl Sagan's Contact, which is where the modern research program came from. A novelist wanting his mechanism to survive expert scrutiny, and asking an expert. A long-running television series built an entire premise around a stable wormhole near a space station, which provided both a reason for travelers to gather and a source of plot. And Interstellar went further than any, computing its images from the equations and generating physics papers in the process. What they share is the need for a shortcut, and what they generally omit is the exotic matter, the stability problem, and the fact that a working one would also be a time machine, which would ruin most plots. A short chapter cataloguing the errors, because knowing them makes the real thing clearer. The tunnel. There is no corridor with walls. There's a sphere and a very short passage, and no visible structure of any kind. The swirling. There's no motion, no turbulence, no luminous vortex. A wormhole would be perfectly still and emit nothing. The flat opening. It isn't a disc you could see edge on or go around the back of. It's a sphere, identical from all directions. The instability drama. Mouths collapsing at plot-convenient moments, or fluctuating dangerously. Real instability would be immediate and total, not gradual and suspenseful. The one-way convenience. Fiction usually treats a wormhole as a shortcut only. Physics says it would also connect times, which means the same device that carries you to a distant star could carry you into your own past, a consequence stories almost always ignore. And the absence of the exotic matter problem. In fiction, a wormhole is found or built and then used. In physics, the entire difficulty is what holds it open, and no story I know of addresses it. None of that is a complaint. Stories have different obligations, but the real version is stranger and quieter than the invented one, which is usually the case in this subject. Let's spend a chapter on why the speed of light matters here, because it explains the whole shape of the problem. The limit isn't a property of light, it's a property of space-time, a conversion factor between distances and durations built into the geometry. Light travels at it because light has no mass. Nothing with mass can reach it, because the energy required grows without bound as you approach. But the deeper reason is causality. Because different observers slice space-time into space and time differently, any influence traveling faster than light would arrive before it left, according to somebody's perfectly valid perspective. Here's the concrete version. Two events far apart in space and close in time have no definite order. Different observers, moving differently, genuinely disagree about which came first, and none of them is mistaken. So if you could send a signal to such an event, you'd be sending it into someone's past. And with two such signals arranged appropriately, you could send a message to your own past. Which means faster than light travel, plus the relativity of simultaneity, gives you time travel, always, without exception. That's why any shortcut, a wormhole, a warp drive, anything, automatically raises the causality question. It isn't a separate issue. It's the same issue. There's a rival proposal worth a chapter, because it has a similar shape and a similar problem. In 1994, a Mexican physicist named Miguel Alcubierre, reportedly inspired by watching Star Trek and wondering whether the warp drive could be given a respectable description, published a paper doing exactly that. His approach was the same reverse engineering trick. Specify the behavior you want and calculate the geometry that produces it. He wanted a ship to travel between 2 points faster than light could, without ever locally exceeding light speed. His solution leaves the ship stationary inside a bubble of flat spacetime, and moves the bubble by contracting space in front and expanding it behind. The ship never moves through space. The space around it is reshaped, carrying it along. Locally, nothing breaks the limit. Globally, the journey is arbitrarily quick. It's a genuine solution to Einstein's equations, and it has the same problem as the wormhole, for the same underlying reason. Producing that arrangement requires negative energy density in large amounts, precisely arranged. Early estimates required a negative mass comparable to the visible universe. Later refinements reduced that enormously, into the range of a planet's mass in some optimistic treatments. Still impossible, but by a smaller margin, which is the sort of progress this field measures itself by. Let's step back for a chapter, because the pattern across all these proposals is the same. Wormholes, warp bubbles, a related construction called a Krasnikov tube, which modifies space-time along a route so that the return journey is fast. Various other exotic geometries. Every one of them is a valid solution to Einstein's equations. The theory permits them, in the sense that the mathematics is consistent. And every one of them requires matter that violates the energy conditions, negative energy density, in quantities and configurations that no known process can produce. That's not a coincidence. There are theorems demonstrating it. Any space-time permitting effective faster-than-light travel requires energy condition violations somewhere. So the entire family of shortcut proposals reduces to a single question. Can the energy conditions be violated substantially and in a controlled way? And the answer from quantum field theory is violated slightly, briefly, under constrained circumstances. And there are theorems limiting how much. Which is why physicists tend to discuss these proposals together, and why progress on one tends to mean progress on all of them, and why the obstacle has not moved in 35 years. That's the crux, and it deserves a careful chapter. The energy conditions are a set of statements about how matter behaves, roughly, that energy density is non-negative as measured by any observer, and that energy doesn't flow faster than light. They were formulated in the 1960s, when classical matter was the only thing under consideration, and they seemed obviously true of everything known. They're not derived from anything deeper. They're assumptions, chosen because all known matter satisfies them, and because they enable powerful theorems, including the singularity theorems that show black holes and the Big Bang are unavoidable. And quantum field theory violates them. That's not controversial. The Casimir effect demonstrates it directly. So the classical conditions are known to be false in general, and the question becomes, what replaces them? The answer is a set of weaker average conditions. Statements not about the energy density at a point, but about its integral along a path, which allow local negativity while requiring overall positivity. Those average conditions appear to hold in quantum field theory, and there are proofs in various settings, and they're strong enough to rule out most wormhole and warp constructions. Which is the current state. The naive conditions are false, the refined ones appear true, and the refined ones still forbid the interesting geometries. There's a separate objection worth a chapter, and it's more fundamental than the matter requirement. A wormhole isn't just a curved region. It has a different topology, a different pattern of connectivity from ordinary space. Space with a handle attached is topologically distinct from space without one. So creating a wormhole where there wasn't one requires the topology of space-time to change. And there are theorems suggesting that's problematic. Classical general relativity, under reasonable assumptions, doesn't permit topology to change smoothly over time. The attempt produces singularities or requires closed causal loops, which is a rather deep obstacle. It suggests that even with unlimited exotic matter, you couldn't manufacture a wormhole in a region that didn't have one. You could only find and maintain a pre-existing one. That's why the natural formation route matters. If wormholes exist at all, they may have to be primordial, features of the initial topology of the universe, rather than things anyone could make. Quantum gravity might permit topology change, and the foam picture assumes it does at small scales. But that's precisely the regime we can't calculate. So there are two independent obstacles: the matter required to hold one open, and the question of whether one could ever be created at all. There's a research field that produces headlines about laboratory wormholes, and it's worth a chapter on what it actually does. It's called analog gravity. The idea is that certain physical systems obey equations mathematically similar to those describing curved spacetime, even though no actual gravity is involved. The classic example is sound in a flowing fluid. If the fluid flows faster than the speed of sound at some boundary, sound waves inside can't escape, which is mathematically analogous to an event horizon. Such sonic black holes have been built using flowing water, Bose-Einstein condensates, and optical systems, and they've been used to look for analogues of Hawking radiation, with some reported observations. That's genuinely valuable. It lets certain predictions be tested in regimes where the mathematics is the same, even though the physical situation is entirely different. What it does not do is create actual space-time curvature. No gravity is involved. Nothing is bent. There have also been experiments described as magnetic wormholes, devices using layered magnetic materials to transmit a magnetic field from one place to another, as though it had traveled through a hidden tunnel, appearing at the far end without a detectable path in between. That's a clever piece of engineering with metamaterials, and it's a genuine result about electromagnetism. It has nothing whatever to do with space-time geometry, and the naming caused a great deal of confusion. A short chapter on the pattern, because it recurs and it's worth recognizing. Physics papers in this area often have technically precise titles and abstracts that use the word wormhole in a specific mathematical sense, referring to a solution, a mathematical structure, or an analog. Press releases then compress that. Headlines compress it further. And by the time it reaches a general audience, a mathematical result about a toy model in a hypothetical spacetime has become "Scientists create wormhole." That's happened at least 3 times in the past decade, with the magnetic metamaterial device, with the theoretical traversability result, and with the quantum processor simulation. In each case, the underlying work was legitimate, and the framing was overstated somewhere along the chain. I don't think anyone is being dishonest exactly. Press offices have incentives, journalists have limited space, and the precise version is genuinely harder to convey. But it means the public impression is that wormhole research keeps producing breakthroughs, when the actual situation has been essentially static since about 1990. The geometry works, the matter required doesn't appear to be available, and nobody has found a way around it. Which is a much duller story, and the accurate one. Let's spend a chapter on the researchers, because the motivation isn't what people assume. Very few physicists work on wormholes in the hope of building one. The energy requirements have been understood for decades, and are not regarded as a research problem so much as a closed door. What they work on is what wormholes reveal about the theory. Exotic geometries are stress tests. General relativity is a beautiful theory, and one way to understand a theory is to push it until it produces something absurd, then ask what stops it. The absurdity is the diagnostic. That approach has been remarkably productive. Asking about traversable wormholes drove work on the energy conditions, on quantum field theory in curved spacetime, and on the quantum inequalities, all of which turned out to matter for other things. The ER equals EPR proposal, and the traversability results in the mathematical settings we discussed, are contributions to the black hole information problem, which is one of the central questions in theoretical physics. So wormholes function as a tool for probing the relationship between quantum theory and gravity, in a regime where the two are forced to interact. The travel application is essentially a byproduct of the naming, and the people doing the work are mostly not thinking about it at all. Let's be concrete about what would change the situation, because it's a short list. A definitive theory of quantum gravity would settle it. If the correct theory forbids topology change and forbids sustained energy condition violations, wormholes are ruled out. If it permits either, the subject reopens. That's the main route, and nobody knows when it will arrive. An observational detection would settle it the other way. If a microlensing survey found an event with the signature of negative mass, or if an object thought to be a black hole turned out to have no horizon, that would be transformative. Those searches are running and have found nothing, but the limits are not tight. A laboratory demonstration of sustained macroscopic negative energy would change things substantially, not enabling a wormhole, but showing that the quantum inequalities can be evaded in some unexpected way. And a proof. Someone might demonstrate rigorously that the averaged energy conditions hold in complete generality, which would close the door within known physics. Progress has been made on that last front. Several general proofs exist in restricted settings, and the space for violations has narrowed steadily. So the realistic expectation is that this closes gradually, by theorems, rather than being settled by an experiment. Let's state the position plainly, because it's worth having in one place. Wormholes exist in the mathematics of general relativity. That's not in dispute. There are exact solutions containing them, and they've been studied for 90 years. The original ones, arising in black hole solutions, are impassable. The throat pinches faster than light can cross, and both ends lie behind horizons. Traversable versions can be constructed, but they require matter with negative energy density, in quantities and configurations that appear to exceed what quantum field theory permits by an enormous margin. They would also be unstable to ordinary perturbations, and creating one would require a change in the topology of spacetime that classical general relativity does not appear to allow. And if one existed, it could be converted into a time machine, which raises the causality problems that most physicists expect the universe to forbid. Against all of that, negative energy is real. The energy conditions are not fundamental laws. The quantum inequalities are proved only in restricted settings, and we lack the theory that would decide the question. So the honest answer is, almost certainly not, for several independent reasons, none of which amounts to a proof. Let's go back to Wheeler for a chapter, because he had an idea about wormholes that is genuinely charming. He asked what an electric field would do if space had a wormhole in it, and the answer is that field lines could thread through the throat, entering at one mouth and emerging from the other. Now consider what an observer sees at each end. At one mouth, field lines emerge, spreading outward, which looks exactly like a positive electric charge sitting there. At the other, they converge inward, which looks exactly like a negative charge. But there's no charge anywhere. There's no particle, no source. There's only a topological feature of space with a field threading through it. Wheeler called this charge without charge, and it was part of his broader program of trying to build all of physics out of geometry alone, matter as knots in space rather than things placed in it. He extended the idea to what he called geons, self-gravitating bundles of electromagnetic field held together by their own gravity, which would behave like massive particles while being made of nothing but field and geometry. None of it worked as a theory of particles. Geons turn out to be unstable, and the wormhole charges don't reproduce the observed properties of anything. But the ambition is appealing, and the image is lovely. A pair of apparent charges that are actually two ends of the same hole. Here's a distinction that clears up a great deal of confusion, and it's worth its own chapter. The wormholes we've discussed so far are features of spacetime, tunnels you could in principle travel through, existing in the ordinary flow of time. There's a second, entirely different object that goes by the same name, and it appears constantly in modern theoretical papers. It's called a Euclidean wormhole, and it exists in a mathematical technique where time is treated as an additional spatial dimension, a trick used to make certain quantum calculations tractable. In that setting, a wormhole is a geometry connecting two regions in a calculation, and it contributes to the total probability of some process. Nothing travels through it, and it doesn't exist in real time at all. They appear in quantum gravity calculations as saddle points, configurations that contribute to a sum over possible geometries. And they've become extremely important recently, for reasons we'll come to. But they are not tunnels, and no one working with them imagines anything passing through. So when a paper announces that wormholes solve the black hole information paradox, it's this second kind that's meant, a calculational structure, not a passageway. The shared name is unfortunate, and it's a substantial source of misunderstanding in popular coverage. That second kind of wormhole produced one of the most significant results in theoretical physics in recent years, and it's worth a careful chapter. The problem is the black hole information paradox, which we've discussed on other nights. When a black hole evaporates, the radiation appears to carry no information about what fell in. which contradicts a foundational principle of quantum mechanics. There's a specific way to state the disagreement, using a quantity that measures how entangled the radiation is with the black hole. Quantum mechanics requires that quantity to rise and then fall as the black hole evaporates, following a particular curve. Hawking's original calculation gives it rising forever. For decades, nobody could reproduce the correct curve from a gravitational calculation. Then, around 2019 and 2020, several groups found that including Euclidean wormhole configurations in the calculation, geometries connecting different copies of the system, produced exactly the required behavior. The wormholes contribute at just the right moment to bend the curve downward, giving the answer quantum mechanics demands. That was a substantial result. It suggested that information does escape, and that the gravitational calculation can produce the right answer if you include configurations nobody had thought to include. It doesn't explain physically how the information gets out, and the interpretation is still debated. But it was the first time the correct curve had been derived from gravity, and it reoriented a great deal of the field. There's a related idea from the 1980s, and it's worth a chapter because it's strange and it briefly seemed to explain something important. The proposal was that quantum fluctuations could produce small closed universes, baby universes, branching off from ours and connected by a narrow throat. Sidney Coleman, among others, explored the consequences and found something remarkable. The branching off of baby universes could affect the effective values of physical constants in the parent universe. Specifically, Coleman argued in 1988 that the process might drive the cosmological constant, the energy of empty space, towards zero, which at the time appeared to be its observed value. That was an enormous claim, because the smallness of the cosmological constant was and remains one of the deepest puzzles in physics. The argument didn't survive. Technical objections accumulated, and then in 1998, the cosmological constant turned out not to be zero after all. Dark energy was discovered, and the target moved. But the episode is interesting for tonight's purposes, because it's an example of wormholes being taken seriously, not as passageways, but as contributors to the quantum state of the universe. And that's essentially how they're used in current theoretical work, not as tunnels, but as configurations that affect calculations. Let's spend a chapter on the scale where quantum gravity matters, because it puts the foam picture in perspective. If you combine the three fundamental constants, the speed of light, the gravitational constant, and Planck's constant, you can construct a unique length. It's called the Planck length, and it's about 10 to the minus 35 meters. To feel that, a proton is about 10 to the minus 15 meters across. So the Planck length is smaller than a proton by the same factor that a proton is smaller than a distance of 100 million kilometers. It's expected to be the scale at which the classical description of spacetime breaks down and quantum gravitational effects dominate. There's a corresponding energy, the Planck energy, which is enormous by particle physics standards. Reaching it in a collider would require an accelerator of implausible scale, by some estimates comparable to the size of a galaxy. So the foam, if it exists, is at a scale we cannot probe directly, and probably never will. Which means Wheeler's picture is, and may remain, untestable. Some proposals exist for indirect signatures, accumulated effects on light traveling across billions of light years, which some observations constrain, and none has found anything. And it means the microscopic wormholes that might permeate space, if they do, are so far beyond reach that their existence makes no practical difference to anything. Here's a question that comes up, and the answer is instructive. Suppose a wormhole were too small or too unstable for anything material to pass through. Could you still send a signal, a photon, or a beam of light? The answer is no, and for the same reason. A photon travels at the speed of light, and the throat pinches closed faster than light can cross it in the non-traversable cases. Anything that would let a photon through would also let matter through, in principle. The traversability condition is about the geometry, not about what you're sending. Which is worth knowing, because it closes an appealing loophole. There's no communication-only wormhole that avoids the exotic matter problem. The traversable versions in the mathematical settings we discussed do allow information transfer, but as we said, only when the two ends are already connected by an ordinary channel, which defeats the purpose. And that limitation isn't an accident. If a wormhole permitted signaling without an ordinary connection, you could arrange to signal into your own past, and all the causality problems return immediately. So the same argument that forbids the travel forbids the message. The universe appears to treat both the same way, which is another sign that causality, rather than engineering, is the real constraint. There's an argument from silence worth a chapter, and it's a nice thought to lie with. If traversable wormholes were possible, if any civilization anywhere in the galaxy's history had built one, the consequences would be enormous. The galaxy is 13 billion years old and contains hundreds of billions of stars, many older than the Sun. If shortcuts through space were achievable, there has been an extraordinary amount of time for someone to achieve them. And a network of wormholes, once established, would be permanent infrastructure. It wouldn't decay when its builders did, so we might expect to find them, or their remains, scattered through the galaxy, detectable by their gravitational signatures. We don't. The searches have found nothing, and the observations of compact objects are consistent with ordinary black holes. That's weak evidence. It could mean nobody has ever existed to build them, or that the technology is achievable but nobody bothered, or that they exist and we can't detect them. But it's consistent with the theoretical expectation, and it's the same shape of argument as the question about visitors from the future. The universe appears to be quiet in exactly the ways it would be if shortcuts weren't available, which proves nothing and is worth noticing. Let's spend a chapter on something the popular version never addresses: how far a wormhole could actually take you. The two mouths can, in the mathematics, be arbitrarily far apart in ordinary space, while the throat between them is short. That's the entire appeal. But the separation of the mouths and the length of the throat are largely independent parameters. You specify both. A wormhole whose mouths are a light year apart with a throat a meter long is a solution. So is one whose mouths are a meter apart with a throat a light year long, which would be a considerable inconvenience. Nothing in the equations preferentially produces the useful kind. There's a further question rarely discussed. How would the mouths get where they are? If a wormhole formed naturally, its two ends would presumably be near each other. Separating them would require transporting one mouth to the destination, at ordinary speeds, taking as long as any conventional journey. Which means a wormhole network would have to be built the slow way first. You'd travel to the distant star by conventional means, carrying one end over centuries, and only then would the shortcut exist. That's not useless. It would make subsequent journeys instant. But the first trip would take exactly as long as it always did, which removes most of the appeal for exploration. A practical objection worth a chapter, and one fiction rarely addresses. If a wormhole connected two places, it wouldn't be selective. Anything at one mouth could pass to the other. That includes light. A wormhole with one mouth near a star and the other in empty space would channel starlight through, illuminating the far side. It includes gas and dust. Interstellar material drifting into one mouth would emerge from the other. And it includes anything unpleasant, radiation, high-energy particles, whatever happens to be present at the far end. So a wormhole would not be a controllable door. It would be a permanent connection with whatever is at one end continuously accessible to the other. Some constructions address this by making the throat very narrow, or by placing the mouths carefully, but it's a reminder that a permanent hole between two regions would have consequences well beyond travel, and that the image of a door which opens when needed and closes afterwards is not what the geometry describes. Let's spend a reflective chapter on why this idea has such a hold, because the disproportion is worth noticing. Scientifically, wormholes are a niche topic. The number of physicists working on traversable geometries with travel in mind is small, and has been for decades. Publicly, they're enormous, appearing constantly in fiction, in documentaries, in casual conversation, with a recognition few open questions in physics achieve. Part of that is the frustration they answer. The universe is very large and very slow to cross, and that's a genuinely disappointing fact about reality. A shortcut is exactly the wish that fact produces. Part is that the concept is graspable. Fold the paper, punch through. Everyone understands it immediately, whatever the mathematics actually says. And part is that it's respectable. Unlike most fictional conveniences, this one has a genuine basis in published physics, which lets people hold it as a possibility rather than a fantasy. There's nothing wrong with the appeal. It's brought a great many people to general relativity. But the honest picture, held alongside it, is that the equations permit the geometry and the universe appears not to permit the matter, and the door has stayed shut for 90 years while people examined it very carefully. Let's go back over the shape itself, slowly, because it's the thing worth carrying into sleep. Imagine two regions of space, far apart. Ordinarily, the only route between them is the long way, through the intervening distance. Now suppose the geometry contains an additional connection, a throat, joining a spherical region here to a spherical region there. From either side, the mouth appears as a sphere. Approaching it, you'd see the far region held in the sphere's surface, growing as you get closer. Inside, you'd be in a region where space narrows to a minimum width, the throat proper, and then widens again toward the other mouth. There's no wall, no tunnel surface, nothing to touch. If you looked sideways while inside, you'd see the two skies wrapped around you, distorted, with the boundary between them somewhere in the middle of your view. That's the whole picture. No corridor, no light show, no sensation. A sphere holding a different sky, a short quiet passage, and then somewhere else. Let's take stock of the history, because the shape of it is instructive. In 1935, a bridge appears in the mathematics as a byproduct of an attempt to describe particles. The particle idea fails. The bridge remains. In the 50s, Wheeler names it and proposes that space-time might be topologically complicated at the smallest scales. In the 60s, the full structure of the black hole solution is worked out, and the bridge is shown to be impassable, pinching shut faster than light can cross. In 1988, Morris and Thorne asked the question backwards and established what a passable one would require. The answer is exotic matter. Through the 90s, the quantum inequalities are developed, constraining how much negative energy can exist, and the requirements begin to look unreachable. In 1992, Hawking proposes chronology protection, giving a mechanism by which such structures would destroy themselves at formation. And since 2013, the subject has reoriented entirely toward entanglement, information, and the structure of quantum gravity, with travel largely abandoned as a motivation. 90 years has produced a clear understanding of what would be required, strong reasons to think it isn't available, and a set of tools that turned out to matter for entirely different problems, which is a reasonable return on a question that probably has a negative answer. Let's take stock, gently, because we're approaching the end of the substance. What's established? General relativity is correct in every regime we've tested. Space-time is genuinely curved, and its equations admit solutions containing tunnels between separated regions. What's very probably true? Those tunnels cannot be held open by any matter that can exist, cannot be created within a universe that starts without them, and would not be stable if they were. What's genuinely open? Whether the quantum theory of gravity permits any of the loopholes, and what that theory even looks like. And what's unknowable at present? Whether anything of this kind exists anywhere in the universe, since we've never observed one, and the searches are not sensitive enough to be conclusive. So the answer to tonight's question, could a wormhole really connect 2 points in space, is, in the equations, yes. In this universe, almost certainly not. And the reason we can't say never is that the relevant physics doesn't exist yet. Which is, I think, a rather comfortable place to leave it. The mathematics is beautiful, the obstacles are real, and nobody needs to decide anything tonight. The subject will close slowly, over decades, by theorem rather than by discovery. And most of the people currently working on it will not be thinking about travel at all. One last substantive chapter, because something survives all of this. Even if wormholes are impossible, the fact that the equations permit them tells us something real. It tells us that space-time is a thing with a shape, that its shape can in principle be exotic, and that what prevents the exotic possibilities isn't geometry, but the properties of matter. That's a genuine insight, and it's not obvious. In Newton's physics, the question couldn't even be asked. Space was a fixed container, and connectivity wasn't a variable. It also tells us that the constraints on matter, the energy conditions, are doing far more work in physics than anyone realized when they were first written down. They forbid wormholes, warp drives, time machines, and several other pathologies, and they were originally introduced as a technical convenience. So the study of impossible geometries has revealed which assumptions are load-bearing. And the exploration produced tools. The analysis of quantum fields in curved spacetime, the quantum inequalities, the work on entanglement and geometry that has become central to quantum gravity research. None of that required the tunnels to be real. The question was productive because it was well posed, not because the answer was yes. Let's spend a chapter on a practical constraint, because it sets the scale of everything. The problem is tidal forces, the difference in gravitational pull between one part of an object and another. Near a strongly curved region, that difference stretches things along one axis and squeezes them along the others. At a wormhole throat, the curvature is extreme by definition, because the geometry has to turn round within a small region, and the tidal forces scale inversely with the square of the throat's radius. A narrow throat means sharp curvature, which means enormous stretching. Morris and Thorne worked out the requirement for a person to survive. The tidal acceleration across a body should be no more than roughly the strength of Earth's gravity. That constrains the throat to be at least meters across and comfortably more. Which has a consequence that runs the wrong way. A larger throat needs more exotic material, because the shell holding it open has more area to cover. So there's a squeeze. Too narrow and nothing survives the passage. Too wide and the energy requirement grows. The window where both are satisfied is where all the difficulty concentrates. There's a version of the black hole solution that seems to offer a passage, and it's frequently misrepresented, so let's be careful. Real black holes rotate, and the solution describing a rotating one, found by Roy Kerr in 1963, has a much richer internal structure than the non-rotating case. Instead of a point at the center, there's a ring-shaped singularity, and in the mathematics, a path exists that threads through the ring and emerges into a different region without ever hitting the singularity. That's the basis of a great deal of speculation about black holes as gateways. The difficulties are substantial. The solution describes an eternal, isolated, unchanging black hole with nothing falling in, an idealization. Real black holes have things falling in, and the interior appears violently unstable to that. In-falling radiation gets blue-shifted without limit as it approaches an inner boundary, building up energy catastrophically. That effect is called mass inflation, and calculations suggest it replaces the elegant internal geometry with a curvature singularity, exactly where the passage was supposed to be. So the expectation is that the interior of a real rotating black hole looks nothing like the textbook picture, and the passage is an artifact. Let's spend a chapter on what would break if those conditions were violated substantially, because it's much more than wormholes. They underpin the singularity theorems, the results proved by Penrose and Hawking in the 1960s, showing that gravitational collapse produces a singularity, and that the universe must have begun with one. Those proofs assume energy density is non-negative. They also underpin results about black holes. That horizon area never decreases. That black holes cannot be split. That the exterior structure is simple. And they support the expectation that space-time is well behaved. That the future can be determined from the present, which is foundational to physics. Wormholes and time machines threaten exactly that. In a space-time containing closed causal loops, there's no consistent way to specify initial conditions and evolve them forward. Determinism fails. Physicists care about that a great deal. A theory permitting arbitrary unpredictability isn't much of a theory. So the energy conditions have been doing enormous structural work, protecting determinism, the singularity theorems, and the orderly behavior of black holes. And they were introduced almost casually as reasonable assumptions about matter. Here's a consequence of negative mass that's rarely mentioned, and it's genuinely peculiar. Negative mass repels everything, including positive mass. But it also responds to forces backwards, because acceleration is force divided by mass, and the mass is negative. So place a negative mass next to a positive one. The positive mass is repelled and accelerates away. The negative mass is attracted, but responds backwards, so it accelerates in the same direction. The pair chases itself across space, accelerating indefinitely, with no energy added, because the two kinetic energies have opposite signs and cancel. That's called runaway motion, and it was noted in the 1950s. It doesn't strictly violate conservation laws, but it's the kind of behavior that suggests something has gone wrong with the assumptions. It's one reason negative mass is regarded with suspicion, quite apart from the energy conditions. It produces situations that look pathological before you even reach wormholes. And it means a wormhole mouth of negative effective mass wouldn't sit still. It would accelerate away from anything nearby, which is a further practical problem for anyone hoping to use one. Let's spend a chapter on the most promising observational test, because it's actually being pursued. When two compact objects merge, gravitational wave detectors record the signal. The final stage, the ring down, is the newly formed object settling, radiating away its distortions in a decaying oscillation. For a black hole, that ring down is determined entirely by mass and spin, and it dies away smoothly, because anything falling inward is absorbed by the horizon. For an object without a true horizon, a wormhole mouth, or one of several other proposed alternatives, some radiation would reflect off the interior structure and come back out, producing faint repeats of the signal at regular intervals afterwards. Those are called echoes, and searching for them has become a small industry since gravitational waves were first detected. Several claims of detection have been made. None has survived scrutiny. The significance has generally evaporated under more careful analysis. But the searches continue. The detectors are being upgraded, and each null result narrows the space for alternatives. It's the most realistic route to evidence, not finding a wormhole, but discovering that something we assumed had a horizon doesn't. A short chapter on an asymmetry that's rarely discussed. There's no requirement that a wormhole's two mouths be identical. In the constructions, they can have different masses, different sizes, different surroundings. Which raises a question: if the geometry is connected, what does an observer at each end actually measure? The answer in the standard solutions is that each mouth has its own effective mass, determined by the geometry near it, and those can differ. There's also the question of what happens when material passes through. Drop something into one mouth, and that mouth's effective mass decreases while the other's increases. The object's mass, in effect, travels with it. Which is consistent, but it means the mouths would evolve as material passed through, and a heavily used wormhole would become increasingly asymmetric over time. None of this matters practically, since the thing probably cannot exist. But it's a reminder that the mathematics has been worked out in considerable detail, and that these objects behave consistently within the theory, even though nothing in the universe appears able to produce them. Let's spend a chapter on another observational distinction, because the images now exist. A black hole produces a shadow. a dark region surrounded by a ring of light, formed by photons that orbit the object before escaping toward us. Two of those have now been photographed by planet-wide radio arrays. A wormhole mouth of the same mass would produce something similar but not identical. The light-bending geometry differs, and the resulting ring structure would have different proportions and different brightness distribution. Several groups have calculated what the difference would look like, and it's subtle. A few percent in the ring diameter, and differences in how brightness falls off at the edges. Current observations aren't precise enough to distinguish them. The imaging is extraordinary, but the uncertainties are larger than the predicted differences. Future arrays, possibly including instruments in space to extend the baseline beyond the Earth's diameter, could improve the resolution substantially. So there's a route. Sharpen the images of the objects we already have, and check whether the ring structure matches a horizon or something else. It's not likely to overturn anything, but it's a real test that will get better. And it's another example of the pattern in this subject. Evidence coming not from finding the exotic thing, but from checking whether the ordinary things are what we think. There's a class of laboratory work worth a chapter, because it produces genuine results and occasional confusing headlines. Light traveling through a material with varying refractive index bends, following curved paths. And the mathematics of that bending can be made identical to light traveling through curved spacetime. That's the basis of transformation optics, designing materials whose properties steer light along prescribed paths, which is how invisibility cloaking devices work in principle. And it means you can build an optical analog of a wormhole, a structure in which light entering one region emerges from another as though it had traveled through a tunnel that isn't there. Such devices have been built at microwave and optical wavelengths. They're clever engineering, and they're useful for testing the mathematics of light propagation in curved geometries. They involve no space-time curvature whatsoever. The light is traveling through ordinary space in an ordinary way. The material is simply bending it along an unusual route. The same applies to the magnetic device we mentioned earlier, which transmitted a magnetic field between 2 points, as though through a hidden channel. These are analog systems, mathematically similar, physically unrelated. And the naming convention has caused a great deal of avoidable confusion. Here's an argument worth a chapter, because it's the kind of consistency check physicists apply instinctively. Suppose you had a wormhole with one mouth in a strong gravitational field and the other in a weak one. Say one near a massive object and one far away. Now drop something into the high mouth. It falls, gaining energy. It emerges from the low mouth, where the gravitational potential is different. Arrange the geometry carefully, and you can extract energy from that cycle, repeatedly, indefinitely, without any input. That's a perpetual motion machine, and its appearance is generally taken as a sign that something in the setup is wrong. The resolution in the careful treatments involves the wormhole's own mass, changing as material passes through, and the energy bookkeeping working out consistently overall. But the general point stands. Connecting two regions with different gravitational potentials creates opportunities for extracting energy that don't exist otherwise, and any consistent theory has to close them. That's another constraint on what geometries can be physical, and it's independent of the exotic matter argument. Physics is full of these consistency checks. If a proposal permits free energy or violates causality, something is usually wrong with the proposal, rather than with thermodynamics. Let's take a reflective chapter, because there's a pattern in how this subject has developed. In the 1930s, wormholes were a mathematical curiosity nobody expected to be physical. In the 50s, they became a possible feature of space-time at small scales. In the 80s, they became a design problem. What would you need to build one? In the 90s, they became a constraint problem. What forbids them, and how strongly? And in the last decade, they've become a calculational tool for problems that have nothing to do with travel, a way of thinking about entanglement, information, and the emergence of geometry. At no point in 90 years has anyone come closer to building one. The energy requirement identified in 1988 is unchanged, and the constraints on it have tightened. What has changed enormously is what the question is for. It began as a description of particles, became a proposal for travel, and ended as a probe of quantum gravity. That's a fairly typical life cycle for an idea in physics. The original motivation fails, the popular version persists, and the actual usefulness turns out to be somewhere nobody expected. One last thought before the recap, and it's the practical one. If wormholes are impossible, and the evidence points that way, then the universe has no shortcuts, and the distances are simply the distances. The nearest star is 4 light-years away, and reaching it means either traveling for millennia or traveling fast enough that time dilation compresses the journey for the traveler, while centuries pass at home. The galaxy is 100,000 light-years across, and crossing it means the same trade at a larger scale. And everything beyond our own gravitationally bound group is receding permanently, so the great majority of the observable universe is already beyond any possible contact, regardless of speed. That's the shape of things, and it's not going to change. Which sounds like a disappointment, and I'd suggest holding it differently. The universe is not a place that can be traversed. It's a place that can be observed, and we can see essentially all of it, right back to the moment it became transparent, from a single small planet, using instruments built in the last century. Looking turns out to be enormously more powerful than going, and it's available tonight to anyone who steps outside. Let's return to Contact for a chapter, because the story's own treatment is unusually careful, and it's a nice thing to know. In the novel, the wormhole isn't built by humans. It's part of an existing network, established by an older civilization, with machines at each end that humans are given instructions to construct. That framing sidesteps the engineering problem gracefully. The characters don't need to know how it's held open, only how to use it. And the description of the passage itself is restrained. There's a sense of enormous speed, and of structures glimpsed at each stopping point, but nothing about walls of light or a corridor. The protagonist emerges near a star, then another, traveling through a series of nodes rather than a single hop, which is closer to how a network of connections would actually have to work, given that each wormhole joins 2 specific points. Sagan also had his physicist friend check the mechanism, which is how the whole modern research program began. There's something appealing about that chain. A novelist wants his plot to be defensible, asks an expert, and the expert's attempt to answer, honestly, opens a research field that runs for 4 decades and contributes to quantum gravity. That's a better outcome than most novels manage. Since Sagan's version involves a network, let's spend a chapter on what that would actually require, because it's rarely thought through. Each wormhole connects exactly 2 points, so a network linking many destinations would need many wormholes, one for each pair you want joined directly, or a hub arrangement with transfers. Each of those would need its own exotic matter, its own stabilization, and its own maintenance. And the mouths would have to be transported into position at ordinary speeds, which for interstellar distances means centuries or millennia per link. So building a network across a galaxy would be a project spanning millions of years, requiring institutional continuity of a kind nothing in human experience approaches. It would also be permanent infrastructure. Once established, the connections would persist whether or not their builders did, which is why the absence of any such network is sometimes cited as weak evidence that nobody has ever built one. That's the practical shape of the fictional premise, and it's a useful corrective. Even granting everything the physics forbids, the logistics would be extraordinary. Which may be why fiction generally has the network already existing, built by someone else long ago. It's the only way to have it without accounting for it. Let me try to state the overall position once more, from a slightly different angle, because it's worth having clearly. There are really 3 separate questions, and they're often conflated. Can a wormhole exist as a geometry? Yes. The equations of general relativity admit solutions containing them, and those solutions are exact and well studied. Can such a geometry be sustained by matter that exists? Almost certainly not. It requires energy conditions to be violated by amounts far beyond what quantum field theory appears to permit. Could one be created where none existed? Probably not, and for an independent reason. It would require the topology of space-time to change, which classical general relativity appears to forbid. 3 questions, 3 answers, and only the first is yes. Add to that the stability problem, and the causality problem, and the observational silence, and the picture is fairly consistent. What keeps the subject alive isn't optimism about travel. It's that the constraints are proved only in restricted settings, that the theory of quantum gravity is missing, and that the mathematics has turned out to be useful for other things. So, beautiful geometry, forbidden matter, and a productive research program built on a question whose answer is probably no. Let's take one more chapter on the physics that is real, because it deserves to be separated from the speculation. Space-time genuinely curves. That's not a hypothesis, it's measured routinely to high precision. Light from distant galaxies is bent as it passes near clusters, producing arcs and multiple images that have been photographed hundreds of times. Clocks run at different rates at different heights, measured across the height of a stack of books, and corrected for continuously in satellite navigation, which would fail within minutes without it. 2 black holes merging 1 billion light-years away shook detectors on Earth by a fraction of the width of a proton, and the waveform matched the predicted shape in detail. The orbit of Mercury precesses by exactly the amount curved spacetime requires. Gyroscopes in orbit precess by the amount frame dragging predicts. So the geometry is real, and it is genuinely flexible, and the equations that describe it have never once been wrong in any regime we've tested. Which is worth holding alongside everything else tonight. The remarkable thing isn't that wormholes might exist. It's that space is the kind of thing that could in principle have a tunnel in it, and that this is established physics rather than speculation. One last reflective chapter, and then we'll begin letting go. The desire underneath this subject is very old and very simple. To be somewhere else without the journey. Every culture has stories about it. Doors that open onto distant places. Paths that shorten for those who know them. Passages through hills into other countries. And the physics version, when it arrived, was received with the same enthusiasm, because it seemed to say that the oldest wish might have a technical basis. What 90 years of careful work has produced is, the shape is permitted, the substance is not, and the universe appears to be arranged so that shortcuts do not occur. Which is a disappointment if you were hoping for a door, and it's also a rather clean answer. Not a maybe hanging indefinitely, but a well-understood set of obstacles, each independently sufficient. And there's something to be said for a universe without shortcuts. It means distances mean something. It means the light arriving from a galaxy tonight really did take that long, and carries a genuine record of that long ago. A universe you could cross instantly would be a universe with no past visible in it. Ours has 13 billion years of history in the sky, precisely because nothing can get here faster than light. If you're still awake, let's walk back through it once more, gently, with nothing to follow and nowhere to arrive. It began by taking away the swirling tunnel. If a wormhole existed, it would be perfectly still, silent, emitting nothing. A sphere hanging in space. The same from every angle, with a different sky held in its surface, and a thin warped ring of your own surroundings wrapped around the edge. You wouldn't travel down a corridor. You'd move toward the sphere. The other sky would grow until it filled your view, and at some point, you'd simply be there instead of here, with no sensation of transition at all. The idea comes from the fact that space isn't a stage. It bends, and it responds to what's in it. And once geometry is a variable, connectivity becomes a question. In 1935, Einstein and Rosen, trying to build particles out of pure geometry, found that the black hole solution could be extended through to a second region, joined by a narrow bridge. The particle idea failed. The bridge stayed. and it's useless. The throat forms, stretches and pinches, closed faster than light can cross it. So nothing can get through, ever, and both ends sit behind horizons anyway. Then, in 1985, a novelist asked a physicist whether his plot worked. It didn't. And the physicist turned the question around. What would you have to add to make a passable one? The answer was exotic matter, something with negative energy density, which would spread light outward rather than focusing it, and which no ordinary substance possesses. And negative energy is real. Two metal plates, a fraction of a micrometer apart, in a vacuum, are pushed together by the quantum jitter of empty space. And the region between them contains less energy than nothing. That's been measured. But the quantities are minuscule, and there are theorems limiting them. The more negative energy you have, the more briefly it can exist, and the sooner the compensating positive energy must arrive. Applied to a wormhole, the requirement comes out at roughly a star's worth of energy, negative, confined to a shell thinner than a proton. Then the further obstacles. Such a structure would be unstable to ordinary perturbations. Creating one would require the topology of space to change, which classical general relativity does not appear to permit. And if one existed, moving one mouth at high speed and bringing it back would turn it into a time machine. Which is why Hawking proposed that quantum fluctuations circulating around the resulting loop would amplify without limit and destroy the thing at the instant it formed. Meanwhile, the subject moved. Since 2013, the interesting work has been about entanglement. The proposal that two entangled black holes are joined by a wormhole, and that geometry itself might emerge from quantum correlations. Those wormholes are impassable by construction, precisely because entanglement cannot carry a signal. And the headlines about wormholes being made in laboratories have referred, in every case, to something else. A magnetic device, a mathematical result in an idealized spacetime, a simulation on a quantum processor. No space-time has ever been bent by anyone. So the equations permit the geometry, and the universe appears not to permit the matter. And the door has stayed shut for 90 years while people examined it very carefully. Let me leave you with some things to rest your attention on, not to learn. Just quiet facts, true right now, while you lie still. In laboratories in several countries, pairs of metal plates are sitting a fraction of a micrometer apart in vacuum chambers, being pushed together by nothing at all. And in the space between them, the energy density is lower than that of empty space. That is the only negative energy anyone has ever produced, and it is very, very small. In the mathematics of general relativity, unaltered since 1915, there exist exact solutions containing tunnels between separated regions. They have been studied for 90 years, and nobody has found an error in them. In archives of microlensing surveys, millions of stars have been monitored for years, and among the thousands of brightening events recorded, there is not one with the signature of negative mass. Somewhere in a theory department tonight, someone is calculating, with Euclidean wormholes, geometries that exist only in a mathematical technique, contributing to a sum over possible shapes of space, helping to work out how information escapes a black hole. And around you, in this room, space-time is very slightly curved by the Earth beneath you, and perfectly smooth and connected in the ordinary way, and going nowhere at all. So here's where we stop. The honest answer to tonight's question is, in the equations, yes. In this universe, almost certainly not, for several independent reasons, none of which quite amounts to a proof. And there's something worth keeping from that. The reason wormholes are probably impossible isn't that the geometry forbids them. Space really can bend, and it really could in principle be connected in unusual ways. What forbids them is the behavior of matter, a set of constraints that were written down as a technical convenience in the 1960s and turned out to be doing an enormous amount of work. The universe seems to permit the shape and not the substance. Let your breathing get slower. You don't have to make it happen. It's already happening, on its own, the way it has all your life. Let your jaw loosen. Let your hands stay wherever they've fallen. Let the bed take your whole weight. Nothing about tonight requires a decision. No door is standing ajar. The distances between things are what they are, and they'll be the same in the morning, and the shortest route from here to anywhere is the ordinary one. You're lying still in gently curved space-time, on a small warm planet, in a universe that is very large and very slow to cross. And there is nowhere you need to be tonight. Sleep well.